Okay, now this is the problem which we'll be solving, and just a minute, please. Bekleyen de yok zannediyorum. Okay, now there is a beam as you see here, okay, and let me read the problem first. The built-up timber beam shown is subject to a vertical shear of 5 kilonewtons, and knowing that the allowed shearing force in the nails is 300 Newton, determine the largest permissible spacing as. Remember, we solved a similar problem previously. Now, but there the surface that connecting the pieces were perpendicular, right? But now here there is a vertical plane, which that plane is not parallel to neutral axis. But anyway, we will start with such cross section. Now look, very briefly, we have this middle board here, right? And then we have these pieces, as you see, and let's attach a coordinate system. Let us say that this is the y-axis and this is the z-axis. So now we know the centroid, okay, of the cross section, and we have nails. You know the nails from the right figure. Now, because there is symmetry, we are going to consider one of these 4 pieces, say this one. Okay. So now look. Hatırlarsınız geçen hafta bunu konuşmuştuk. Let me select the region which divides the body into 2. Now this red line divides the body into 2 and leaves this separate from that. So now we are separating this area, this cross-sectional area, from the remaining. And this cross-sectional area is centroid somewhere here, and it is distance from the neutral axis is y bar, and it is equal to 100 millimeters as clear from the figure. And this is also the neutral axis here. Okay, now look, what was our equation? Our equation was V over IT. But now this is shear equations. Remember, whenever we have nails, pins, whatever, we will use shear flow equation. V Q over I. Okay. So in this problem, I'm just going to write the resultant moment of inertia to save time. So we are looking for the shear flow between these two surfaces along the plane, which is shown by that red line over there. Remember, shear flow equation is this. We have a shear force Vy, then we have Qz and Iz. Remember this equation. Okay, so as a result, we are assuming that there is a shear force here, which is Vy, and as a result of this, there must be a moment attached with that, Mz, okay? Although these are not clear from the statement of the problem, but we should have these. I'm indicating the direction to make the problem further clear. Now, in this problem, Iz can be calculated easily for the whole cross section, and that's equal to 167.18 times 10 to the power 6. Okay, please calculate this by considering those areas. Then, okay, then the remaining is very simple to calculate. We only need the Qz. Remember, Qz is the moment of area about z-axis, first moment of area, which is simply y bar times a. Now, y bar is clear for that rectangular area, which is equal to 100 millimeters. You can easily verify from the problem. And area is clear. Look at the figure. It is 50 millimeters by 50 millimeters. Okay. So from here, you can easily calculate the first moment of area, which is equal to, in this problem, 250,000. Okay. So this is the first moment of the cross-section area. Therefore, by using that red line, which indicates a plane at the end, we determined the shear flow through that. So, very simply, the shear flow gives us the following. Q is equal to Vy, which is given in the problem as 5,000 newtons. Öyleydi galiba, değil mi? Yes. And then the Q value, which is 250,000 millimeter cube, şu küp olacak, 2 değil. Divided by the moment of inertia, 167.18 10 to the power 6. So from here, what you get is 7.48 newtons millimeter. Arkadaşlar, this shear flow is the shear flow on the plane shown by this red line. This red line indicates a transverse plane, okay, a longitudinal plane. We just see it, it's an intersection with the screen, okay? So on this plane, we have such a shear flow per unit length. Look at the nails. The nails are transferring the shear between these two boards, between the two wooden parts. Therefore, if nail is equal to, do you remember the equation? The force nail is equal to the shear flow times their spacing, or the spacing is equal to the shear force carried by each nail over S. It is given that each nail can carry 300 newtons, and then S is equal to, Q is equal to 7.48 newtons millimeter. Therefore, for this case, the spacing must be 40 point
Hocam,
millimeters.
yazdığınızda Q olmayacak mıydı orası? F''in altı.
Evet, olacak. Düzelteyim onu. Şunu kastettin değil mi? Okay.
Evet.
This, as your friend said, this must be Q. Let me write in red to make the error clear. Okay. Anyway, this gives you the spacing. Shortly, when there is rivet, bolt use shear flow to indicate or to find the spacing between them or any as related question. Okay. Now, let me extend this problem a little. If the surfaces were glued, okay, could you answer me if the surfaces, okay, connected or, okay, are glued, let me say, then what would I do? Say that they are not joined together by the nails, but they are just glued to each other. Then what is the concern now? Okay, let me tell you, find the shearing stress. Find the average shearing stress. If this is my question, now there is no nail, there are glued surfaces, therefore tau now, which is xz in this problem, average is equal to Vy Qz Iz times T. The only unknown here is the T. For this problem, T is equal to, who is going to tell me, what is T? Var mı hatırlayan T'nin ne olduğunu?
50.
Efendim?
50.
Yes, T is the length of this red line. It is the plane or intersection of that plane with the transverse section, which is 50 millimeters, as your friend said. So by taking T as 50 millimeters, we can say that the shearing stress here is equal to 149 kilopascals. Look, if we are talking about stress, then we have to have completely connected surfaces. But nails are just transferring the shear from one part to the other through their bodies. Is this clear? Burayla ilgili açık olmayan herhangi bir şey var mı?
Yani ben bir şey sorabilir miyim?
Evet.
Bu son yaptığımız kısımda değil de bir sorunun ilk statement'ına gelebilir miyiz? Hocam burada bir tane nail, iki tane bloku, 3 bloğu birbirine sabitliyor ya.
Hayır. Her nail 2 blok birbirine sabitliyor.
Ya bir ortadaki olan bir de en sağ ve en soldakiler.
Yani 4 tane parça var burada. Nail'ler o 4 parçayı ortadaki bloka sabitliyor.
Evet, hocam burada yani shear'in bölgesi olarak bakarsak bir nail'e etki eden iki farklı shear plane yok mu? Mesela y ekseninde kırmızıyla çizdik ya, y
Evet.
eksene paralel bir çizgi.
Evet.
Onun bir de y eksenine simetri olan diğer tarafındaki shear foil'de almamız gerekmez mi? Çünkü iki taraftan da kuvvet uygulanmaz mı buna?
Şimdi burada kuvvet aşağı doğru burada. Bir tek kuvvet var. O da şu. Body'nin üzerinde on the cross section there is one shear force. It is in this direction. Right. This is the shear force. Is this clear?
Evet.
This shear force creates shearing stress on this cross section. The shearing stress on the cross section are as follows. Şöyle çizeyim. Pin olmadığını varsayıyorum. Onu birazdan yapacağım. Because of this shearing stresses on the cross section, we have such shearing stresses, right? Zero at the top, here increasing like that, then decreasing, and these are the shearing stresses. Oldu mu?
Evet.
Eğer shearing stressi soruyorsan. But since there is a nail here, the forces created by these shearing stresses are transmitted to the other through the nail. Şimdi
Evet.
soruyu bir kez daha tekrar eder misin?
Hocam o sağ tarafta force transmitliyor ya.
Evet.
Aynı şekilde bunun sol tarafında da olmaz mı aynı
Oluyor
işlem?
tabii. Burada var.
İşte bunun için force'u ikiye bölmemiz gerekmez mi? Yani mesela şu an
Hayır.
cevapta kaç bulduk hatırlamıyorum.
Hayır. Bölmemiz gerekmez. Çünkü biz şu Q'yle burada Q'yle sadece şunun üzerindeki şeyi bulduk. Q'yu bulduk. Bunda da aynı Q var.
Ha,
Yani
tamam.
şurada Q ile burada Q aynı.
tamam.
Öyle değil mi? Çünkü Q ayırdığımız alanla ilgili bir şey. Sadece bu alanı ayırdığımız için biz bu ikisi arasındaki Q'yu bulduk. Aynen söylediğin gibi bu iki alan yani bu parçayla bu alan arasında gene aynı büyüklükte Q var. Anlatabildim mi?
Anladım hocam. Evet,
Dolayısıyla
şimdi anladım.
kuvvet bu Q ile ilintili. Burada kuvvet aynı şekilde bu Q'lar buralarda da var. Dolayısıyla Q ile bulduğun sadece ilgilendiğin, kestiğin yüzeydeki shear flow. Ve oradaki neyle ilgileniyorsun. Açık oldu mu?
Oldu hocam. Teşekkürler.
Tamam. Peki. Dolayısıyla esasında aynı Q'dan 4 tane var burada. Altlarda da var ama biz nereye ayırırsak o ayırdığımızla diğer arasındaki yüzeydeki Q'yu buluruz. Ve oradaki çiviye bolta onu çözmek için kullanırız. Oldu mu? Peki. Başka sorunuz yoksa devam ediyorum. Şu Q'yu düzelteyim artık. Şimdi konu kısmına geçelim. Galiba bu son konumuz bu chapter'la ilgili. Burayı biraz lütfen dikkatli dinleyin. Hem de ekrandan da belki biraz zor olacak ama neyse. Shearing stresses. Now look, we will be talking about the team members. Shearing stress in thin walled members. Now, actually, in thin walled members, instead of talking about shear, we talk about shear flow. But still, let's investigate the shearing stresses. Okay. Now, one example is an I-beam. Consider this I-beam like that. Okay. Now, this is the I-beam that we are now trying to find the shearing stress on it. And being different than farz edin ki bu düzgün bir I-beam arkadaşlar. Tamam mı? Okay. Now, on this I-beam, assume that we have such a shear force Vy, and as a result, a coupled moment like this Mz. We know that they are always coupled with each other. And let's say that we have such a coordinate system. This is X, this is Y, and this is Z. Further, somewhere here we have the centroid, okay? of the cross section, centroid of the cross section. Say this is centroid. And then, of course, we also have the neutral axis passing from the centroid because there is no radial load now. This is the neutral axis. Now look, please look carefully. This is not a cross section, this is a cross section of beam, but it continues, okay, just a portion. Now, if I remove a portion from here, this time the situation is a little bit different. I'm just removing such a portion from here. Say that this distance is delta x, because this is along the x-axis, and this is the thickness of the member. Look, if I isolate this portion from the remaining, like that, okay, now, because of this moment, which always occur on the member because of the shearing stresses, will create normal stresses on this place, as you all know, say compressive, sometimes tensile, at the bottom tensile. Okay, so we have such stresses on the surface. And also, on the other section, we have also, on the other face, we have also shearing stresses, normal stresses due to moment. Is this clear? There always exists normal stresses if there's a shear force in this manner. Okay, now look, if I write the force balance as we did many times before, okay, as in the previous derivations. Now, assume that sigma x2, this is, say, sigma x2, the normal stress distribution on the front face, say, okay, sigma x2, and say that this is sigma x1. And let us also assume that in magnitude, sigma x2 is greater than, in magnitude, sigma x1. How can I satisfy the equilibrium? Who is going to tell me? Denge yok. Nasıl sağlarız? Var mı bir öneriniz? Geçen kısımları dinlediniz mi? Malzemenin diğer tarafı nereden bağlı? Şuradan bağlı. There must be a shear force here, right? Oldu mu arkadaşlar? For equilibrium. And this shear force, as a result, is determined with this equation. The same equation, derivation is the same. Delta Vx, as before, Vy times Iqz over Iz times delta x. Now we found the same equation, but now there is a stress, there is a shear force on a vertical plane. Okay, so if I take a cubical element from here, look, if I take a cubical element from here, yani şöyle yapalım. Şuradan bir kübik eleman alayım arkadaşlar. Okay. Buraya. Okay. On this cubical element, takip ediyorsunuz değil mi? I have the following stress state. Mustafa Metehan, İçöz, takip ediyor musun?
Evet hocam.
Peki. Şimdi bunun özellik stresleri söyler misin bana, shearing stresleri?
Bakayım. Shearing stresleri. Üstten ve alttan olması lazım hocam.
Peki başka fikri olan var mı içinizde? Osman Bora, sen ne diyorsun?
Bizden taraftaki yüzde shear stresi olacak hocam.
Shear'ı soruyorum.
Evet.
Burada
Geliyor
bir
mu sesim?
force var mı arkadaşlar şurada?
Var.
Var. Bu shear force hanede bir shear stresi olması gerekir mi?
Gerekir.
gerekir. Demek ki şöyle bir shear stresim var. Eğer bu varsa ne var? Şu var. Değil mi? Diğer taraftan bu var. Bir de bu var. Bu shear stresler dışında ayrıca bir normal stresim var. Doğru mu? Momentten ötürü. Kübik eleman üzerinde. I also have this normal stress other than these. Okay. This one. Arkadaşlar dersi takip edin lütfen. So, what about this shearing stress? It is tau x z. Is this clear? Now look, I have a shearing stress tau x z. Other than these, I also have this shearing stress on the body, like that, okay, which is tau on the x-plane in y direction, but generally we ignore this. Okay. In thin wall members, we ignore this shearing stress, generally, when compared with tau xz. So, for these problems, the shear flow is obtained with this equation again. It is Vy Qz times Iz. And for these thin members, tau is equal to Q over T. Okay. And for the given section, we have a shearing stress tau with subscripts xz that's equal to Vy Qz Iz times T. Okay. Any question? Anlaşıldı mı arkadaşlar? Bakın burada yeni bir stres daha çıktı şimdi.
Hocam o tau xz mi, tau zx mi?
Fark etmez.
Göstermiyor.
Simetrik olduğu için yani genelde ekseti kullanıyoruz. Ama o yüzeyin normali şuraya bakarsan esasında z. Zx. Ama simetri bu da ekset olduğu için şu yüzeydeki genelde simetrik olduğunu bildiğim için iki tane ayrı yazmaktansa bir tanesini kullanıyorum. Oldu mu? Ama
Evet.
esas notation senin söylediğin gibi Excel ama dikkat edersen hiçbir zaman simetriyi dikkat alarak iki ayrı convention kullanmıyoruz. Buraya kadar tamam mı arkadaşlar? Bakın. Burayı iyi takip edin lütfen. Çünkü burayı kaçırırsanız buralarda sıkıntı yaşarsınız. Şimdi bu albümü bir daha çizeceğim size. Tekrar. Ve stresleri göstereceğim. Ignore olanları da göstereceğim. Yani demin maviler ignore dedim bakın. Now look. We have this beam. This I-beam, right? The stress state on this I-beam is something like this. Ben şöyle elle hızlı çiziyorum. Now, if we are looking for the flange of this I-beam, and we are assuming that there is a shear force Vy on the cross section. Burayı takip edin lütfen. Vy, pardon. Şunun rengini değiştireyim, karışmasın. Bu arada şunu biraz daha inceltelim. Okay, say that we have a shear force Vy. Mavi alamadık. Aşağı doğru Vy. And also we have a moment mz. Now, because of this Vy, on this area, look, on this area, or symmetrically on this area, at this point, we have two shearing stresses. One is this, in this direction. The other one is in this direction. Bu yön nereden geldi derseniz, bakın, şu shear, look at the force, direction of this force. As a result, direction of the shearing stress on the front face, this one. So, one is towards middle portion and the other in the opposite direction. Why this time force is on the other face? Or, if you consider the whole area, onu da bunun üzerine çizmeyeyim, karışmasın diye bir tane daha çizelim. Or, if you take such a section, bir saniye arkadaşlar. Umarım takip ediyorsunuzdur. Nihayet kalem alabildik galiba. Okay, now I'm again taking the same I-beam, but this time I am looking not for the previous cross sections, but the cross section on the web portion, right? So now, okay, this is the I-beam once more, okay. Say that this time I am trying to find the shearing stress on this cross section. So now this is the area that I am related at this point. Okay, so on this cross section, assuming that we have the same loading as before, so now say that we have the shear force Vy again, okay, and moment Mz again. This time, the shearing stress here should be in the downwards direction, and it is again tau. Now look, these are tau x, z, and they are equal to, ya da şuraya yazayım. These are tau x, z. Peki bunu size soracağım. Koordinat sistemini bir kez daha çizeyim ki sizin de bir fikriniz olsun. Bakalım ne kadar buraları takip ediyorsunuz. Mehmet Çağrıeti. Mehmet, şu iki shearing stresleri tek tek yazalım. Önce şuradakinden başlayalım. Subscriptlerini bana söyler misin? Tau. Sesin gelmiyor ama. Peki. Senin sesini duyamadım. Doğan Güneş sen söyler misin?
Evet.
Şu birincisi.
Bilmiyorum hocam, pardon.
Arkadaşlar dönemin sonuna geliyoruz. Daha bunun subscriptlerini yazamıyor musunuz? Var mı içinize söyleyecek olan?
Tavuğu ekset değil mi hocam?
Tabii ekset, evet. Peki buradaki? Soldaki?
O da aynı.
O da
Aynı.
aynı. Okay, so this is tau exet. Equation is Vy Qz over Iz times T. What about this? This is Vy Qz Iz times T. So what's the difference? The second one is minus. Why? Because x is positive but z is negative here. Peki şunu söyleyin. Tau, yes. X,
XY.
y. Equation is the same. Vy Qz over Iz times T. But it's again minus. Oldu mu arkadaşlar? Okay. Şimdi bakın yönlerine. This is towards the middle portion. This is towards the middle portion and this is in the downwards direction. As a result, actually, in thin walled members, we, instead of showing stress, generally show the shear flow. And the shear flow has the same direction with the stress, obviously. So, if you look at the directions of the stress from the above figures, you will see that it is just like a fluid flowing in a channel. Okay, just like fluid flowing in a channel. What I'm saying is this. Now, look at the above figure. The first stress is towards right. So we have Q as follows. Now it increases, it is 0 at the end. It increases towards the middle portion. The same thing is valid. It is like that, increases towards the middle portion. Then it flows in the downwards direction, decreases again, then turns back to this direction and becomes 0 at the end. Then the same thing is valid for this portion. Q flows in this direction and becomes 0 at the end. Okay, so this is, if this is Q1, if this is Q2, now here we have Q, which is equal to Q1 plus Q2. Burası anlaşıldı mı arkadaşlar? Şimdi bakın. Üstte Q1 sağa doğruyken alttaki niye sola doğruyken alttaki niye sağa doğru? Bunu kim söyleyecek?
Shear force'u Y direksiyonunda eşitlemek için, yani Z direksiyonundaki force'ları sıfırlamak için.
Şimdi yukarıda biz şöyle kabul ettik değil mi? Bakın. Üst tarafa şuraya bakın. Üstte we said that sigma 2 is greater than sigma 1. Burası oldu mu? That's why Vx is in the positive x direction. At the bottom, bakın arkadaşlar, at the bottom, what's the direction of these normal stresses this time? Who's going to tell? Now, here there is compression. At the bottom, there is tension. So their directions are opposite. Sigma 2 now is in this direction. Okay. At the bottom. And this is in this direction. Since this is greater, Vx must be opposed to that. That's why. I mean, mechanically, everything is size 5. So, for thin members, you can assume that you can calculate the shear flow as follows. The best way is this. You have your shear force on the cross section. We know that our shear force is in this direction, Vy. So in the middle portion, I have the same direction, the Q direction of the Q is the same with that. Then just determine the others by thinking a fluid flowing in a channel. Anlaşıldı mı arkadaşlar? Peki. Şimdi gelelim şeye. Closed kısma geçmeden biraz daha açık olsun diye tekrar ayrıyım çizeceğim şöyle. Umarım takip ediyorsunuzdur. Look, this is the I-beam that we are talking about. Okay. Now, I'm going to draw two graphs, the shear flow and shear stress. Remember, for the shear stress, previously, we obtained the distribution. Okay, and we said that the shear stress distribution here is such that now it increases, suddenly makes a step, okay, because of changing T, and it reaches maximum somewhere here. So this is, okay, tau xy graph. On the other hand side, if you draw the shear flow Q, okay, the Q would be in such a quantity in the middle portion. Okay, so there are two graphs here. This is the distribution of the Q, and the other one is the distribution of the shear stress. Is this clear? Now, if you do the same thing for the flange region, like that, you will see that this time the Q is increasing towards the middle portion. So say that this is the Q axis. So this is the variation of the Q. It is 0 at the middle portion, but increases towards the middle, 0 at the ends. And the shear stress for this part, now, as we have just determined from the above, has two different distributions. One of them is that, and the other one is that. So this is tau xz distribution. Is this clear? Now, then Q flows like that, greater here, smaller here, then turns back here, it becomes very large here, smaller, then turns toward the ends and become 0 here, and turns to left and becomes 0 here. This is the direction of the shear flow with the same direction. Now look, on this cross section, arkadaşlar buraya lütfen dikkat dinleyin. On this cross section, we refer to if buraya bakın arkadaşlar lütfen. If you need to design the member, if you need to design the member with respect to this point, there are two stresses acting. One of them is TXZ, the other one is TYZ. We ignore this stress and only decided the design with the XZ as I just mentioned above. Bilmem anlaşıldı mı? Sorunuz var mı? Peki. Bir de close box'lara bakalım o zaman. Arkadaşlar hiç tereddütünüz var mı bunlarla ilgili? Aklınız bu derste de umarım. Şimdi bir de close box'tan bahsedeyim. Bu tarafa doğru, sona doğru azalıyor. Okay. Now, this is for an I-beam. If we had a closed box, the situation changes a little. Say that we have such a box. The only difference is this. Okay. If your beam has such a cross section, now look, you have just a closed box cross section like this. This is a cross section of your beam, and it goes like that, right? And say that we have the following axis on this beam. So this is the centroid of the beam, say, and here is the x-axis. Okay, then this is the y-axis and this is the z-axis. Now, if you have a shear force on that beam, lütfen iyi takip edin. If you have a shear force on that beam, and then a coupled moment as a result, and if you need to find the shearing stress somewhere here, for example, what you do is this. You just remove an element from here. Look, I am looking for this point, say. Noktayı takip edin. So then I remove a portion from here, but this line is not enough as before. I cannot divide this body into two by a single line. So to remove, I am using another portion from here. And then now let's take such an element, of course, this is an infinitesimal element, to discuss the situation. Now, if I take this element and draw here, okay, then what I have is this. I have this removed portion here, okay, like that. Şu olsun. Now, on this portion, biraz daha sağa çizeceğim. On this portion, there are moments, there are normal stresses due to moment. We know it. If there is a shear stress, shear force, there must be moments on it. So, we have normal stress on this face. Şöyle çizeyim biraz daha kolay olsun diye. And also normal stresses on this face because of moment. Now, say that these are sigma x2 and these are sigma x1. Again, assume that sigma x2 is greater than sigma x1. Now, to satisfy force equilibrium, again, we have to apply shear forces. So, as before, we have a shear force on this face, which is delta Bx on this face, okay, here, delta Vx, but this time there is another surface which is connected to the body, and that is this. So we have also delta Vx here. Is this clear? So therefore, the shear flow here is determined with the following equation. Q is equal to the same equation. Q is equal to Vy Qz over Iz, but this time we have this on both sides. Don't forget, with this Q, hani biraz önce sormuştunuz ya iki tarafta var mı diye, burada gerçekten iki tarafta var şimdi. On both sides, because we are dividing the member into two by using two surfaces right now. And as a result, as an extension of this, tau xz on the surface is again Vy Qz over Iz times t. It is both plus and minus if we are using both faces. Here, t is equal to 2tb. Now, let me just put dimensions. Here, I am taking an element which is equal to delta x, but now I am saying that this is tb now. You have to use two tb's being different than ib. As a result, the shear flow on this box is something like this. Onu da çizip bu kısmı, burayı arkadaşlar bir üzerinden gidin. Tam anlayıp anlamadığınızı emin olamadım çünkü. Now, what about the shear flow? First of all, look, if you take such a portion from this element, okay, this is our box, right, which we have the cross section, and this is also the same box, the same cross section at the same location, nothing changed. I'm using two figures for that purpose. Okay. On both of these boxes, we have the following coordinates. Okay. Undo. This one, Z, Y, Y, and we are assuming that there is a shear force Vy here. Okay. A coupled moment Mz. Shear force Vy, attached moment Mz. Now look, if I am asking the stresses at this point, I have to divide the body into two and select this area for Q. If somebody asks you the stress at this point, arkadaşlar buraya bakın. If somebody asking the stress at this point, what we were doing before, we were drawing a line to divide the body into two, but this is not enough, as in the other beams. So use the symmetry also and take this cross section for calculating Q. Okay, so as a result, here we have these shearing stresses on both ends, this one and this one. This is tau x at the end. And here we have these shearing stresses from the same loading. This is equal to tau xy, and tau is equal to Q over T for such members. Okay, now what about the flow of Q? Let me draw it as the final part of this derivation. For a thin-walled member, for a thin-walled member, if there is a shear force applied on that member, so say that this is the z-axis and this is the y-axis, and say that this is the shear force given in the problem, okay, which is coupled with the moment, so Vy, Vy, and this is the moment. Look, we look at about the stress distribution in the front two figures. Now, to draw Q, again, assume that there is a channel where the fluid is flowing. So here and here we have maximum shearing stresses. But look at this area. As this area becomes smaller and smaller, tau xz becomes smaller and smaller. This is tau xz. Arkadaşlar bakın bu tau xz'i nereden buluyorduk? Şuradaki tau xz'i v q over it'den buluyorduk değil mi? As this area becomes smaller and smaller, q is the smallest. So there is no shear stress at this point in terms of tau xz. But as you go size, it increases like that, then turns its direction. Here it goes to the left, okay, and then turns direction. Then, as if a fluid flowing in the channel, it decreases first, then turns this direction because of the reason which I mentioned, becomes zero here, and this is the Q distribution on the cross section of the member. Why the direction is changing here? Because if moment is compressive above, tensile here, so the directions of the stress are changing. As a result, direction of the larger stress has changed. So their differences now has an opposite sign when compared with the previous one. Buraya kadar anlaşıldı mı arkadaşlar? Umarım anlaşılmıştır. Lütfen bunun üzerinden bir gidin. Bir dahaki ders buradan başlayalım. Çünkü bundan başka burada bir konu yok. Sadece problem çözeceğim. Arkasından da bir sonraki chapter'a başlayacağım. Böylece esas stres diyen chapter'ımızı bitirmiş olduk. Sorunuz var mı? Bunlarla ilgili.
Bir şey sorabilir miyim?
Bunlarla
Yukarıda,
mı? Evet.
evet, yukarıda şey çizmiştik ya. Element
Arkadaşlar
çizmiştik
ders
ya.
bitmiştir bu arada. Evet. Pardon, nereyi sordun?